Okay, so now we're going to pick back up and discuss how we can use that inheritance or being able to plot different data sets as a way to enhance our plotting capabilities for our statistical models. So, as I said, this is not really the statistics class. This isn't the class in which you will learn the appropriate model, how to implement the appropriate model. But I do want to show you a very, very useful tool given a very basic statistical model. So we've seen the decline with the miles per gallon on the highway as a function of the engine size. So let's just say we're going to model that with a linear model. So the R code for that is just linear model, data, and then my Y variable followed by my various predictors. So I'm just going to do a single predictor here, which is going to be the engine size. I can look at the summary, and what I get is that there is an average decline of about 3.5 miles per gallon for every unit or every one increase in the engine volume size. Now what's useful is that I can take that data set and actually make various predictions from my linear model. So using this regression equation, I want to predict using my model is M here, the, uh, the prediction values from my model. So if I open up my data frame, what I get is that it predicts that a vehicle with this engine size should have about 29.3 miles per gallon on the highway. And in fact, it has 29, so not too bad. But then based off of this one with a slightly larger engine, it predicts 28 miles per gallon. It actually has 31, so it's a misprediction. But you can see that it's just using the two input data points that I provided. We could do a variety of others, but this is just to illustrate what we can or what we can do. But now we have a potential of two different y variables. One being our actual highway miles per gallon, but another one being our model prediction of those. So we can see how well does our model actually predict the raw data. So I can have my ggplot, specify my aesthetics, where X is my engine size, Y is my miles per gallon on the highway, add the raw data points, and then I'm going to add a line. And I'm going to keep the same data, but I'm going to override the aesthetics and say X is equal to the same engine size. But now my Y is equal to my prediction. And what that gives me is my linear regression line from my statistical model. So you might say, well, Nathan, we already had that with our GM smoother, right? We were able to do plus GM smooth, can still do GM smooth. That equals LN. Same darn thing. What's interesting or cool about that? And the reason is that this allows you to graph your actual model that you use. Very rarely are you going to have a singular X and a singular Y for a statistical model that you might use in your papers or for your final ultimate analyses. Whereas here with the prediction tool, you can actually use your final statistical model, predict your statistical model's predictions, and then graph them directly onto your data. So it gives you a more powerful way to connect what your statistics are telling you to what your data actually looks like. It gives you a much greater range of flexibility. So say, for example, you were using logistic regression or you were using some other more advanced statistical technique, like maybe a mixed effects model. This would give you the capabilities to graph a mixed effects model for both your fixed and random effects and plotting your actual statistical model on top of your raw data and seeing, is my statistical model an appropriate fit for my actual data by being able to visualize it. So say, for example, here we added in more variables. Like say we wanted to have the drivetrain in addition to the engine size. We can see that drivetrain is also a significant predictor. Then I can run prediction. So predict using this model what it expects that to be. And then using the exact same code as before, I now am able to look at how does my statistical model predict what's actually going on here. So what we see here is that we have the same slope for each one of my drivetrains, right? So I have drivetrain forward, drivetrain four-wheel, drivetrain reverse. But this doesn't really seem to fit very well for what my reverse or rear wheel, sorry, not reverse, my rear wheel drivetrain seems to be showing me. It seems to fit really well for my forward, and it seems to fit relatively decent for my four-wheel, but not so much my rear wheel drive. So how do I potentially change the slope here between my drivetrain and my displacement volume? And that is what a statistical interaction is. So let's say, for example, we wanted to see, well, is there a statistical interaction? So I can take my first model, my second model, and I can compare my first model. Oops. We need an additional library I forgot to add in here. And don't worry, you don't have to worry about necessarily being able to understand the statistical tests here. Essentially, I'm fitting a linear model with an interaction, a linear model without the interaction. And then we're basically just looking at, oops, the ANOVA table to see, is my interaction significant? And it does actually indicate that there is a significant interaction here. So let's do a prediction. So we'll call prediction 1 is a prediction from my first model. Prediction 2 is a prediction from my second model. And let's see, does one model actually predict my data any better using a visual or graphical sort of look at that? So we can create plot 1, which will provide prediction 1. Then we can create plot 2, which will use my second prediction, or my prediction using my other model. And then, sorry, I'm missing another library. So ggpubber is a library that allows us to, there are a variety of tools that allow us to paste multiple plots together. ggpubber is a simple one that I like to use. It has the argument ggarrange, and you can specify plot 1, plot 2. You can say the number of columns that you want it to be. So I can say ncol equals 2. I want them to be next to each other. And what it gives me is plot 1 and plot 2. So what I have in plot 1 is my statistical model that includes an interaction term. And in this plot, I have my statistical model that does not include an interaction term. So if you ever wondered, what does it mean when I actually have an interaction in my data or not? And how am I actually interpreting it? And I know we talk about an interaction is that the level of one variable influences the effect of another variable. But this is literally what the interaction is showing us, is that this slope is different for this drivetrain than it is for the other drivetrain. So with no interaction, all the slopes have to be the same. With an interaction, the slopes don't have to be the same, and one slope might be different. So this significant interaction is basically saying that this relationship of engine size and fuel efficiency for a rear-wheel drive vehicle is different than it is for a forward-wheel drive vehicle. So this means that for your fancy sports cars, you can increase the engine size bigger and bigger and bigger as a rear-wheel drive vehicle without actually having much of a hit to the overall fuel efficiency, at least on the highway. So this allows you to plot and compare different statistical models visually to help confirm whether your interactions seem to make sense and whether your model is the most appropriate fit to your data. So for me, I personally find this to be a tremendously powerful tool because while I like, the numbers from a statistical model, this is what tells me whether my statistical model is appropriate versus this, in comparison to that, versus just looking at the numbers and scanning for is p less than 0.05. There's a variety of reasons why that is problematic, which we don't need to go to in this class, but nonetheless, we can go from there. Anyway, the nice thing about the predict is that it allows us to do predictions in addition to the data that we already have on data that we don't actually have. So it allows us to extend our statistical model to predict things that we may not necessarily have. So for example, let's say we wanted to expand our data set into so that each drivetrain would extend out to an engine size of 7 liters. So what you can see is that the forward wheel drives only end right here, and the rear wheel drives continue out to here, and the forward wheel drives end at 6. If we wanted to, we could create a new data set using expand.grid, and we say that the displacement is 1 through 7, and the drivetrain is each of the unique drivetrains. When we just look at this, all this is doing is just giving us 1 through 7 forward, 1 through 7 four-wheel, 1 through 7 rear wheel. Then we can take our prediction of our model with the interaction and say, use the new data and the new data frame. Then we plot our raw data in the same way that we did before. But now our lines come from a different data set, our new DF data set, and we plot the prediction. And what this gives us is essentially the same figure we have here, but it allows us to have the predictions at the full range of the scale for each one. So that we could see that if we had a rear-wheel drive vehicle at 2 liters per minute with this 2 liters with this interaction, it would be the least efficient vehicle. However, when we get to our 6 or 7 liters, even our 5-liter engines, then the rear wheel is actually the most fuel efficient. So it allows us to see what this interaction actually looks like across the entire span, and highlights that's probably why engineers tend to put our big sports cars in our rear wheel drive, our typical cars are our front wheel drive, and then our 4 wheels are kind of just because we want 4 wheels. Now this is 2 tools for graphing distributions of data. So this is a typical histogram. We can specify different bin widths, which basically, as you can see, specifies how much or what span of our x-axis it's going to be graphing. So we could do 1 mile gallon, and you can see that this specification almost suggests possibly a bimodal distribution of our y variable. Our density plots are kind of nice. It again shows our distribution, but shows it as a nice little line, which highlights that actually we seem to have a bimodal distribution. We have one chunk of fuel efficiencies over here, and then another chunk of fuel efficiencies in this scale, which is kind of what we had been seeing so far, to be honest, is we kind of have this chunk over here, and then another kind of like specific chunk in this range over here. And that's what's being picked up by this. But if you need to graph to inspect the normality of your distribution, or if you have any issues with your distribution, a density plot is a really nice way of doing that. But this is also a simple way to do a histogram in a traditional fashion for inspecting the distribution of your variables. We can also use a library called ggridges. ggridges gives us a slightly more interesting density plot. So I have our density plot specified by our four-wheel drive, our rear-wheel drive, and our rear-wheel drive vehicles. And it shows that our forward-wheel drive vehicles actually are relatively normally distributed with a mean somewhere around 26, 27 miles per gallon. Our four-wheel drives tend to have a relatively normally distributed data around this like 17 mile per gallon area. Although we do have another kind of little bump up here in the 25, so it's almost bimodal. And then our rear-wheel drives also seem somewhat bimodal based off of this. But this is really a useful tool because um, a lot of our assumptions of normality are not whether your pure y variable is normally distributed. So again, not a statistics class, so we won't go too much into this, but it's whether your y variable is normally distributed at each of the levels of your predictor variables. So if you have various levels of predictor variables, then this ggridges is a really useful tool to kind of break out your distribution based off of each of these caveats. So here we have it broken out by our drivetrain. So we could also break this out further based off of uh, what was our other variables, sorry. Class, possibly. Yeah, class. So we could also break it out by class if we then see if that's normally distributed when we break it out by class and drivetrain. Or cylinder size, 4 versus 6 versus 8. We could look at those to see if we get more normally distributed data in those cases. Okay, then our last video is going to be on faceting, and we will be right back with that.